Now, ANOVA is useful for a number of things, but one thing is if the comparing the means for more than two populations, more than two samples, so three or more samples. So let's see an example. At a community college, a mathematics department has been experimenting with 4 different delivery mechanisms for content in their intermediate algebra courses. One method is the traditional lecture, method 1. The second is a hybrid format in which half the class time is online and the other is face-to-face, method 2. The third is online. The fourth is an emporium model from which students obtain their lectures and do their work in a lab with an instructor available for assistance. Method 4. Okay. So there's 4 methods. That's all. To assess the effectiveness of the 4 methods, students in each approach are given a final exam with the results shown in the accompanying table. Ooh, let's look at the table. Numbers. Oh, look at all those numbers. That's too much to look at outside of StatCrunch. Let's put it in StatCrunch. I'm being facetious, but really, we're going to do all this stuff in StatCrunch, so that should be the immediate thing to do with all of this data. Bring it in StatCrunch. Okay, do the data suggest that any method has a different mean score from the others? Well, the null hypothesis in situations like this would be that all the means are equal to each other. The alternative is that at least one of them is different. So that's the only way we phrase the null and the alternative in this case. So the null is that all the means are equal. So this is mu1, this is mu, the population mean for approach 1, equals mu2, equals mu3, equals mu4. I don't know what they are, but they're all equal. That's the null hypothesis. It's just claiming they're equal. It doesn't claim they are equal to any particular number, just that they're all equal. The alternative is that at least one of them is different. They could all be different from each other, but at least one of them is different. Okay, that's the null and the alternative. Requirements for an ANOVA procedure. We need to have case samples independent of each other. That's necessary. So we have, in this case, we have 4 samples. We need to have 4 simple random samples, and each one is coming from one of the 4 populations. That's another requirement. The populations, they don't have to be normally distributed with the same mean, but they should be normally distributed or close to normally distributed with the same variance at least. And that's the 3 requirements. They should not be from the same population. So we're given an ANOVA table. Cool. Maybe we don't have to run it ourselves, but you know what I'm going to do? I'm going to create my own ANOVA table, because how do I know that that's right? I'm going to go into StatCrunch. I'm going to go to Stat. I'm going to go to ANOVA, a one-way ANOVA. And I'm going to select all 4 of these and click Compute and make my own ANOVA table, because I can. So let's just compare. We've got 3, 702, 67. Yeah, okay, fine. The numbers are the same. But just wanted to double check it. That's how you create an ANOVA table from data. So, but they're giving it to us here, so that's nice. So we're basing it on the p-value. This is a p-value of 0.223. Should the null hypothesis be rejected? Well, that's a pretty high p-value. We would normally only reject, and here we're using a 0.05 significance level. This 0.223, that's not greater than that's greater than the significance level. That means we do not reject. Do not reject. There is insufficient evidence to support H1, the alternative hypothesis. So let's see. Side-by-side box plots. That's what they look like. I don't trust that. I'm going to make my own box plots. All right, let's go over to StatCrunch and just practice making side-by-side box plots again. Box plot. I'm going to select all 4 of them, and I'm going to do horizontal box plots and color scheme, basic 7 colors. I don't need to do anything else. Just click compute. Okay. Yeah, I guess that's right. That matches pretty much. Although it looks like I think that in their box plots they're putting the mean as that line instead of the median. Let's just check. I'm gonna put the mean in as green lines. No, I feel like they messed up on that top one. I don't know. I feel like that's off. This is not the same. But I'm not gonna get too obsessed over it. They're telling me that those are the box plots, so I'll just take it. Okay. So what do we want to ask? Shown side by side, do the box plots support the result obtained? Like, from these box plots, is it reasonable to assume that all these populations have the same mean? Yeah, I mean, pretty much. They're like the middle that middle 50%. That's overlapping on all of them. There's a common overlap, even in mine. So I would say, yeah, it supports. It doesn't. It doesn't show that they have significantly different means. So I would say, yeah, it's fine. Interpret the p-value. Since the p-value is not less than alpha, since it's greater than or equal to alpha, that there is insufficient evidence that any one method is more or less effective than the others. Yeah, that's how you interpret a p-value in this case. Verify the residuals are normally distributed. Okay, so let's look at the residual plot. Make a normal probability plot of residuals. So let's go back here. Let's go to stat. Let's go to actually on our ANOVA, or one-way ANOVA. I want to graph a what's called a QQ plot of the residuals. A QQ plot of residuals is what we're asked for here. I'm going to click compute, and I didn't select my variables. A QQ plot of residuals. It's going to be the second screen here. This is I'm not getting those little curvy bound things that it has here, but what I've got here is residuals versus normal quantiles. I'd like to flip this around, and I don't know if I am able to do that. This is a little bit frustrating. Okay, you can see that on these examples we've got residual as the x-axis and z-score on the y-axis. It looks this plot looks like it looks a bit like A and B, but I'm gonna look at B first. The problem is that my axes are flipped, so I'm gonna have to use my imagination to flip this stuff around. Unfortunately, that's kind of hard to do. I've got so we're trying to look at this pattern to see. So we have this line that goes down, this diagonal line, and we want to compare this. So this looks pretty good, although that point is not too close to the line. I'm going to go back to the other one. So you have to imagine, you flip it over and see if it would match. No, this isn't the right shape. I'm going with this with choice B. That's closer. I know you had to do a mirror image to see it, but it's there. Anyway, what does a QQ plot mean? If these dots are along the diagonal, then that pretty much tells us that, yeah, the populations are pretty much normally distributed. The plot is approximately linear. I mean, that's fine. We don't have to be too picky. It is approximately linear, so I'm going to say, yeah, we have normality in our samples.